In this video, we're going to look at Pulleys and Atwood's machines and kind of introduce them and explain what they do. But before we get too far into it, we need to talk about two assumptions that we're going to make. And these will be assumptions that will hold for this unit, but in future units they might change. So first, we're going to assume that ropes and cables are massless, and you'll sometimes see this presented as light, as in lightweight. And we're also going to assume that they don't stretch. So if you pull on a rope, it's not going to stretch, it's going to stay taut. Next, we're going to assume that pulleys are frictionless and massless. So in other words, there's no friction with the pulley spinning, and itself, it doesn't have very much weight. So you might also again see the word light used here to indicate that the mass is inconsequential. Like I said, this will hold true for this unit. There will be some places later where it may not, but if you're ever trying to do math in this class, you can make these assumptions. Okay, so as a reminder, tension is a pull force that is constant throughout a rope or cable. In other words, whatever the tension is at one point, it's the same throughout. So if you imagine I've got a rope here and say I'm pulling some box, the force that I pull here means that every point on the rope, it's going to feel tension in both directions. And what we end up having is that when we get to the very end of the rope, it exerts an equal and opposite force pulling towards it. So tension is constant throughout, so whatever the Ft is here, it's the same here in the middle and the same at the other end. So ropes are really nice because they basically let you put a force somewhere else that you're not touching directly because you transfer that force through the rope. A pulley is a device that redirects the tension force without changing the magnitude of the force. So in other words, it lets you take a downward tension force and turn it to sideways, like we saw in that first, in that lab that you would have done. That you can put a downward force and change it into a horizontal force. We'll talk about a few more examples later. Now, these two only apply because of our assumptions. So if the rope stretches or if the rope has mass, tension is not constant throughout. If the pulley has mass or has friction, it will change the magnitude of the force. But again, for calculations in this unit, none of those are going to matter. It'll just be in some of the later units you might have to talk about it qualitatively, like if we added mass, what would happen to the force? And when we get to those problems, we'll talk about them. But for now, you can assume that all of this is true. So an Atwood's machine combines ropes and pulleys to give a greater, I mean, they don't technically have to do this, but typically they're going to be giving a greater or lesser effect than usual. So for example, if I have something like this, so I've got two pulleys here, you can see those two circles, and I've got this tension rope throughout, and then I've got this block. So now, if you pull down on this rope, what's going to happen? You know, naturally we'd expect that the rope's going to get shorter, and so this block and setup gets pulled up. But if you look at the free body diagram for this pulley or for the block, it has Fg pulling it down, but it's got two rope forces pulling it up because the rope on either side is going to keep it from falling. And what's that force? It's Ft, which is however hard you're pulling on it. So in other words, you can get twice the power, twice the effect of your tension force if you have it run over a couple of pulleys like this. You can also do the same idea like this if we insert a couple extra pulleys here. And then attach both of these to our block. Then you'll notice how many ropes you have going up. You've got 4. So that free body diagram, which is really sloppy here, let me redraw that. You've got 4 FTs pointing up and the force of gravity pointing down. So in other words, this setup gives you 4 times the amount of tension force pulling upwards. So this is what you would have for an Atwood machine. There's ways to do it for less, like to reduce the effect by half, things like that. But I just want to kind of give this idea if you can see where these might be useful or that idea. In the next couple of videos, I'll actually solve some example problems with this, and you'll see the calculations that come into play.